If you remember, hydration means what? To hydrate something, right? Hydration means to add water. You want to hydrate, okay? Alkynes are triple bonds. Now, triple bonds perform a special temporary step when a product is formed that the other ones don't usually perform. Okay, so if we have an alkyne and we have two R groups attached to it, we have R and R prime. That just means an alkyl group, like one CH3, one could be CH2, CH2, CH3, just carbon groups attached to it. One's different than the other. We add water, we open up that triple bond, okay? And we add H and OH, okay? And then we have a double bond left. This compound that is formed is an intermediate compound. It's unstable, okay? So being unstable, boy, it's going to change its form. This is what's called an enol. En because they're double bond, which is right here, and OL because it's an alcohol, which means it has an OH group right here. So oxygen is much more electronegative than carbon. So it's going to pull the electrons in a double bond towards itself. So what it's going to do is pull the electrons towards that bond. So this bond is now going to become a double bonded oxygen, and this hydrogen here is going to feed back to that carbon. So you get a structure which is an aldehyde or a ketone. An aldehyde is this carbonyl group. This is called a carbonyl group. A C double bond oxygen, that's a carbonyl group. If the carbonyl group has two carbons attached to it, carbon here, it's called a ketone. Okay. If one of those groups is an H group, it's called an aldehyde. And that's it. That's how alkynes work. Okay. The triple bond opens up and you have a double bond with an OH group and an H because you hydrated it. You added H2O. Okay. And it formed what's called an enol. Enols are unstable and it forms either an aldehyde or a ketone. Okay. So hydration of alkyne is a more complex process than we've been dealing with because there's an intermediate group formed. Okay. The initial product formed is not stable. That's your enol. And again, it got its name because En for double bond. Remember, double bond is E and E. So they shortened it up. So double bond is En and OL is alcohol, OH group. So the enol is both an alkene and an alcohol. That's what we call it, an enol. It's rapidly isomerized, which means it doesn't change the molecular structure. It doesn't change the molecular structure. Same number of carbons, same number of oxygens, same number of hydrogens, but it changes its shape, its configuration. Okay. The final product is going to be either an aldehyde or a ketone. Remember we said aldehydes have a carbonyl group and attached to it is a hydrogen on that carbon. A ketone has two carbons attached to it on both sides. One carbon on both sides. So let's do an example and we'll show you some specific examples here. So it says write a balanced equation for the complete hydration of each of the following alkynes and specify where the product's going to be an aldehyde or a ketone. All right. So what's going to happen? We're doing hydration. Hydration means adding water. So H2O. So if we draw this out a little bit, there's 3 carbons. Okay. This is CH3. This is CCH. I have too many. I put the wrong in the wrong place. Wait a minute. I don't want to confuse you there. Okay. C carbon, triple bond. This was CH3. This is C, this is CH. There's our compound. So we hydrate an alkyne. That triple bond opens up. So we lose this bond here. and we form across that bond. We have two things. We have H and OH. So we put OH, and it's going to form either. You have to do it both times because it form two products. It could go to either one, or we could switch this with H and OH. Okay, and this is an enol, so it's unstable. So the bond's going to come up here and form a carbonyl group. Okay, and that's what happens. So let's move this out of the way, and let's do our example. We'll show exactly what happens here. So this triple bond opens up, and now we have a double bond. We put the OH on this side and the H here, and the other possible product is the H and OH here. Okay, you can form two different products. Both these are enols. So then the double bond, being more electronegative towards oxygen, forms to there, and you get your carbonyl group being formed. And the same thing here. Your oxygen pulls those double bonds, and you get your carbonyl group formed here. Okay. So the intermediate steps are enols, and those are unstable. Okay. So now, is this product on this side here, is this a ketone or an aldehyde? Anybody want to, huh? Anybody want to guess? Got a 50-50 chance. It's either ketone or an aldehyde. This is your carbonyl group. Is there two carbons attached or a carbon and hydrogen attached? There's two carbons, right? A carbon on each side. So this is a ketone. A ketone has two carbons, one carbon on each side attached. On the bottom one, here's your carbonyl group. The carbon has a carbon attached and it has a hydrogen attached. So if one of the groups attached is a hydrogen, it is an aldehyde. Okay, is that making sense? Sort of. Is everybody following the difference here between addition with this one? Someone do a thumbs up or a yes or something.
Yes.
Perfect. Got it. Let's make sure everybody can hear what I'm saying. So there's your enol, there's your ketone, there's your enol, and there's your aldehyde. Okay. I think this is where we left off as we were doing this. Okay, same thing again. You're doing a hydration reaction. Hydration means plus H2O, and you want to know if it forms an aldehyde or a ketone. Right? So here's our triple bond. We're going to tack this triple bond. On one of this, we're going to add OH, and the other side, we're going to add hydrogen. There's our H2O, or OH and hydrogen. So two different products. Okay. So you open up a triple bond. That leaves us a double bond. We added the OH to the first carbon, the H to the second one. The other way we did it was add the H to the second carbon, the first carbon, and OH to the second one. Just put them in two different places. And when we recognize we have a double bond with an OH group attached by that double bond, that's an enol, because these are both enols. And we know enols are unstable. Okay, so this double bond is going to sling up here, and this double bond is going to sling over there. And it's going to form a carbonyl group. So here's your carbonyl group, and here's your carbonyl group. All right. So now all you got to do is determine whether they're aldehydes or ketones. So this top one here. Okay, here's your carbonyl group. Is this an aldehyde or a ketone? Anybody want to take a guess?
It's a ketone.
Perfect. It's a ketone, exactly. It's a ketone because it has one carbon on this side and one carbon on this side of the carbonyl. So this is a ketone. Bottom one, is this one a ketone or an aldehyde?
It's also a ketone.
It's also a ketone. Perfect. Okay, because it has a carbon attached and another carbon attached. So it's also a ketone.
Professor, I had a question.
Sure.
So when it on the enol, why does the double bond swing down to OH?
Okay, because when you have a situation where you have an OH group and a double bond here, there's a lot of electrons in this double bond right here. Oxygen is much more electronegative than carbon, which means it wants the electrons more. It's going to attract electrons more. That's responsible for hydrogen bonding in water. Its polar property thing like that is that OH group is very electronegative. So the electrons are going to pull towards that oxygen rather than the carbon. So they're going to sling away from that and form the double bond with oxygen instead. Because oxygen wants electrons more. Remember electronegativity? Remember that term?
Yeah, I remember.
Sort of. Electronegativity is a series, it's on your periodic table. You can look at the different electronegativity of the elements. And all it is how bad something wants an electron. The more it wants electrons, the higher electronegativity. Oxygen is like a 3.5 and carbon is like a 2.2 with electronegativity values, with 4 being the highest. Okay, so the great concentration, because remember a double bond is 4 electrons. Okay, each bond is 2 electrons. So there's a lot of electrons in a double bond. So those electrons are going to go to the element that wants them the most, and oxygen wants it more. So it pulls the electrons out of the double bond to form the double with the oxygen itself, because carbon doesn't attract them as much once it's formed.
Okay, that makes sense. Thank you very much.
Oh, you're welcome. No problem. That's why enols are unstable. And they don't exist. It's just for a short time and convert over. No problem. So there's your enol. This is a ketone, like we said. This is another enol, and this is also another ketone. Enols are always going to form either ketone or an aldehyde. Okay. Any questions on the triple bonds, the alkynes? Do you want me to do another example of one?
Yeah.
Yeah, another example. They're kind of hard to grasp. And I do have another program set up here. And let's see how we did it. There you go. I mean, I was working with one of the students. I found I have a better program for it, and I think got my program down pat here now. So let's get an example. Let's say we have CH3C, CH3C, triple bond C, bonded to hydrogen. And let's put a hydrogen in here too. Okay, there's a compound, right? So
Okay.
that's 3-methylbutene as a compound. So here's our triple bond. Okay, and what we want to do is we're going to do a hydration reaction. So plus H2O. Okay, so we're going to open up the triple bond, and it's going to attack where those electrons are. And water is, we got to remember, water is H and OH. Those are the 2 parts of water that we're going to form, that are going to attack. So one of them could be this combination here, CH3, CH3H, and we open up our one of the bonds. I put it in the wrong place, didn't I? There you go, fix that. Okay, there's C, and now our bond opens up to form that. Okay, on the first one, we're going to put an OH. The next one, we're going to put a hydrogen. And we're going to do the exact same thing, just switching to H and OH, because it can attack either of the carbons. Okay, there's 2 ways it could attack that bond. So you got to count for both ways. And this is the exact same compound that we drew there. Okay, and this time I'm going to put the H here and the OH here. Remember we had Markov's rule about hydrogen likes hydrogen when attacked. These don't matter because it's such a short-lived structure, it doesn't matter. So they're roughly 50-50 when they attack. So on this one, we put the OH on the left. This one, I put the OH on the right. Okay, so 2 compounds are going to be formed. It's just random. Okay, these are both enols. Okay, because there's a double bond carbon next to a carbon with an OH group. So enol, the ENE is double bond, the OL is an alcohol. An alcohol is an OH group. Okay. So what's going to happen? The electrons in this double bond are going to go towards the oxygen. The electrons in this double bond are going to go towards the oxygen. So enols are going to rapidly isomerize into either an aldehyde or a ketone. If it goes this one, let's do the top one here. CH3, CH3, C, let's see, there's an H here too. And then this becomes our double bond where those electrons have swung over. And this becomes, we have our hydrogen here, and our hydrogen gets added here, CH3. Okay. And the next one, we have our CH3, CH3, H, CH, okay, C, double bonded oxygen. Remember, it swings towards the OH group. And our hydrogen and the hydrogen from the OH group. So two compounds are going to form. Remember, the electrons swing towards the OH group and make that a single bond and create a double bond with the oxygen. So here's our what's called our carbonyl group on both of our compounds. So now look at the top one closely. What's attached to the carbonyl carbon? Is that an aldehyde or a ketone?
Ketone.
Ketone, perfect. Because there's a carbon attached here and there's a carbon attached here. So that is a ketone. Okay. Look at the aldehyde group on the bottom one. This carbon. Is this aldehyde or a ketone?
An alcohol?
Perfect. It's an aldehyde because there's a carbon attached and a hydrogen attached to the carbonyl carbon. That makes it an aldehyde. Perfect. All right. Does that make a little more sense?
Yes.
All right. Any more questions with that? I can erase it and I can use the screen next time. Okay. I finally figured out how to get a blackboard up here so I can write and draw and stuff now. And I think it's going to work. All right. And then we'll go back. I should go back to my lecture now. So we'll see how this works. Should go back to right in the same spot. Yeah, we're back. A little bit further back, but that's okay. It's not too bad off. All right. So here's where we're at. We did that one. And we did the second one. And here's where we left off. All right. Any more questions on alkanes or alkynes, I mean, on hydration? Okay. Next, we're going to do hydrogen halides. And halides are fluorine, chlorine, bromine, and iodine. Group 7 in the periodic table. Those are your halogens. So they're halides. Hydrogen halide just means there's a hydrogen attached to the halogen. Okay? And they can be added to a double bond. So this is hydrohalogenation. Okay, we're adding an H and we're adding a halogen. So hydrohalogenation. Okay, so here's our double bond again for our reaction. And X represents a halogen, chlorine, bromine, fluorine, or iodine. Any one of those, take your pick. Okay, so what happens is this double bond opens up, the H goes to one, and the X goes to the other one. So here's the H, there's the X. Your double bond opened up for that. Okay, they both attack the double bond. That's simple reaction. Okay, it's not as complex as the alkynes. Okay, so you're taking an alkene and you're producing a Well, you have a hydrogen halide you're adding to it, and you're producing an alkyl halide. Alkyl is your carbon group. That's all it is. Alkyl is your hydrocarbon, and the halide is the halogen. So you're taking an alkene and you're producing an alkyl halide by adding a hydrogen halide to it. So here's our example. This is ethene, 2 carbons, 1 double bond. We're going to have an H and a Br. So it's going to attack carbon, and it's going to attack this one. Okay. And you're going to produce 1 bromo ethane from an ethene, I'm sorry. Now, if we switch these around, if this hydrogen went to this one and the bromine went to this one, would that form a different compound?
No.
No, the exact same compound. So only one product is formed. It does that because this is a symmetrical compound. If they're symmetrical, it doesn't matter which end of the double bond it adds to. It's going to be the same compound. Perfect. So ethene, and it goes to hydrogen bromide, goes to 1 bromo ethane or bromoethane. All right, so hydrohalogenation, H, halogen, so an H, chlorine, bromine, iodine, or fluorine, and then genation, add to it. Get rid of that in case it's going to interfere with my, come on. So an alkene, alkenes are double bonds, can combine with a hydrogen halide, like hydrogen bromide or hydrogen chloride. The reaction is an alkyl halide. Okay. Now we got Markovnikov's rule again. If it's not symmetrical, same exact rule we did last time. You don't have to remember Markovnikov's rule. Just remember that hydrogen likes hydrogen. The carbon with the most hydrogen is going to be the major product where the hydrogen bonds to that. Hydrogen likes to go to hydrogen. Easiest way to remember it. Okay, so here we got propene, and we're going to add HBr to it. So we're going to go through double bond, attack there, and attack there. So one way, we're going to open the double bond, a bromine is going to attack to the left side, and a hydrogen on the right side. The other way is if the hydrogen goes to the left side of the double bond, and the bromine goes to the right side. Those are 2 different products. You always know you're going to have 2 different products when the starting material is asymmetrical. Look at the double bond here. This double bond has hydrogens over here and hydrogen CH3 over here. It's not the same. So it's different on both sides. If it's different on both sides, you're going to have 2 products. If it's symmetrical like it was last time, then you only have 1. Okay. So here's where our bromine went, to the left with the double bond, then our hydrogen, and then we switched. Hydrogen went to the left side, bromine went to the right side. All right. So are we going to have 50-50? We're going to have major, minor? What are we going to have?
Major, minor.
Yeah, major, minor, because they're different on a different amount of hydrogens. Okay. So is the top product going to be a major one or a minor one?
Major.
Perfect, major, because there's hydrogens here. And this hydrogen that's added, this is your added hydrogen, has 2 hydrogens here. When the hydrogen adds here, this is your added hydrogen, there's only 1 hydrogen. And hydrogen likes hydrogen. So this is going to be your major product. This is going to be your minor product. Okay. So we started with propene. Okay. The major product was 2-bromopropane. Here's number 1 carbon, number 2 carbon, number 3. It says propane. And at the number 2 one, there's a bromine. That's the major product. The minor product. What's the name of the minor product?
Just bromopropane?
Perfect. Bromopropane or 1-bromopropane, either way you want to write it, it's fine. Bromopropane, that's your minor product. But you need to see the difference in how they're added. When this adds, there's 2 hydrogens here. When this one adds, there's only 1 hydrogen here. So this is going to be your major product because the hydrogen added seeks more hydrogens. That's Markovnikov's rule. And that tells you if it's a major or minor product. Okay. Write an equation showing all the products from hydrohalogenation of 1-pentene with HCl. All right. 1-pentene is what? How many carbons?
5.
5 carbons. Penta's 5. All 1 double bond at the number 1 position. So there's 1-pentene. Okay. So there's 5 carbons. 1, 2, 3, 4, 5. And a double bond at the number 1 position. So here's your product we're starting with. Is this product symmetrical or asymmetrical?
Asymmetrical.
Right, it's asymmetrical, right? It's not the same on both sides of the carbon, of the double bond of carbon. So that way it's not symmetrical. You're going to have 2 different products. Okay. HCl, one of them, the hydrogen is going to go here and the CO is going to go here. The other one, the CO is going to go here and the H is going to go here. We just switch it. Okay. So you open up our double bond. We put the chlorine to the left, the hydrogen to the right. Put the chlorine to the right and the hydrogen to the left for the other product. All right. And then we look at them. Looking at those 2, is the top or the bottom going to be major minor, or is it going to be a 50-50? If it's major minor, which one's going to be the major, which one's going to be the minor?
The top is major, the bottom is minor.
Perfect. Exactly right. Because this hydrogen that was added, okay, has 2 hydrogens existing on that carbon. This hydrogen that was added on the bottom one only has 1 hydrogen existing on there. And hydrogen likes to be by hydrogen. So the top one's your major product, bottom one is your minor product. Who wants to name the top one?
Two chloropentane.
Perfect. 2-chloropentane. How about the bottom one?
Chloropentane.
Chloropentane or 1-chloropentane. You got it. So your major product is where hydrogen has more hydrogen. The hydrogen attaches to the carbon with the most hydrogens already attached. And that's 2-chloropentane. Bottom one is your minor product. And it's 1-chloropentane or chloropentane. Either way is fine. Okay, where the chlorine to the number 1 position. Because this hydrogen here, there's only 1 hydrogen attached to the carbon, whereas the other one had 2 attached to it. Okay. Now, when we're going through these, it's easy to watch me do it. Okay. I make it look real simple. It's not real simple. It takes practice. Do the practice problems in the book. If you have problems with them, email me. We can set up a little Zoom meeting. I can go through with you, make sure you understand it. But make sure you try to do some of these on your own, because you're going to understand it when I do it. Okay, I enjoy teaching it. I'm going to make it look real simple. But when you sit down and do it by yourself, go, what did he do again? So try by yourself also, and just send me an email. We'll set up a Zoom meeting. I can walk you through everything. I got no problem with this. I'm almost always around somewhere where I have an internet connection. And perfect. All right, balanced equation for hydrobromination. Okay, so we're going to add HBr, okay, to an alkene. So 2-pentene. Again, penta is 5 carbons, and there's 1 double bond. How do we know there's only 1 double bond? I keep saying that, but how do we know that?
There's only 1 number out front.
1 number out front, and it says ENE. If there were 2 double bonds, there'd be a second number out front, and it would say diene. If there were 3, there'd be 3 numbers out front, and it would say triene. So that's how we know there's only one double bond, because it just says E and E, and there's only one number out front. Perfect. So 2-pentene is 5 carbons with a double bond at the number 2 position. Okay, so here's your 5 carbons. Okay, your double bonds right here at the number 2 position, and we're going to add HBr. Okay, and this is asymmetrical. It is not symmetrical. So we know we're going to have 2 different compounds. Now they could be 50-50 or they could be major minor. We don't know that part yet. So we're going to add H, we're going to attack the carbons of the double bond. We're going to add H to one and Br to the other one. Okay. So let's add Br to the left and then Br to the right. H to the right, H to the left. Those are our 2 possibilities. Okay, and we're going to look at the compounds that are formed. Okay, do we have 50-50 or do you have major and minor? If you have major and minor, which one's major, which one's minor?
50-50.
You have 50-50, perfect. Okay, we're going to have 50-50. Everybody should see that when hydrogen here, let's put a different color. When hydrogen bonds to this one, there's 1 hydrogen on that carbon. When hydrogen bonds to the other one on the bottom, there's 1 hydrogen. So it's the exact same. Doesn't matter which way the bonds attack, whether bromine's on the left or bromine's on the right of the double bond. Okay, it makes no difference because the hydrogen is the same. So it's going to be a 50-50 split. There is no major or minor. All right. Who wants to name the top one? Any guesses?
2-bromopentane.
You got it. Perfect. 2-bromopentane. And it's 50%. And the bottom one is going to be what? It's a what bromine is this? What carbon is this one here?
3.
Perfect. So 3-bromopentane. You got it. And it's 50-50. See, it's not so hard when I do it, right? Propene. Okay, we're doing a balance equation for the hydrobromination. So HBr again. Okay, of propene. Propene is how many carbons?
3.
3. Propane is 3 carbons. So propene, 3 carbons with 1 double bond is at the number 1 position. So this is propene. This is 1. This is 2. This is 3. Okay. And we're going to add HBr. It's going to attack our double bond. So it's going to come here. And this is going to be an H. Come here. This is going to be Br. And it's going to switch. This is going to be Br. This is going to be H. Okay. That's how we get our 2 different compounds. Because this is asymmetrical. Because one has CH3, one has an H. So I want to go back. Let's go back the whole way though. We'll come back to it. We'll figure this out. All right. We're back. All right. So the bromine's attacked, H on one side, Br on the other side. And so Br is on the left of where the double bond used to be, which is right here. And Br is on the right. Hydrogen's on the right. Hydrogen's on the left. All right. So looking at this, is this going to be 50-50 or major minor?
Major minor.
Major minor, because they're different now. Okay. Which one's going to be major, top or bottom?
Top.
I think the book puts everything on the top that's major. It's not going to always work like that. All right. It's major because when the hydrogen adds to the right, there's 2 hydrogens. When the hydrogen adds to the left, there's only 1 hydrogen on that carbon. So this is your major compound form, and this is your minor compound form. Okay. So if we're going to name these things, the top one would be, what would it be?
To bromopropane.
Perfect. Perfect. 2 bromopropane. Okay, and that's your major product because of where this hydrogen adds, there's 2 hydrogens on there. Okay, what's the bottom product going to be?
Bromopentane.
Bromopentane, or 1 bromopentane, same thing. And that's your minor product. You guys are getting this too. Very good. 2-methylheptene, a little different. Okay. Let's draw it up here in the corner so before we show exactly what it is. And we're going to hydrobromination. Heptene is how many carbons?
7.
7 carbons. Perfect. 3, 4, 5, 6, 7 carbons. At number 2, there's a methyl group. A methyl is 1 carbon. And at number 3, there is a double bond. Okay, and there's only 1 double bond because there's nothing in front of here that says di or tri or tetra or penta. Okay, and there's only 1 number in front of it. So we know there's only 1 double bond. So we know we're going to tack right here and right here. And it's going to be hydrobromination. So one's going to be an H, one's going to be an Br. One's going to be a Br, one's going to be an H. That's how we set it up. So let's draw it out here like you can see a little bit better. So this is 2-bromopentane on the left here. And you can see we're going to tack that double bond just like we said, right there and right there. And we're going to put a Br on the left, H on the right, or an H on the left and a Br on the right. Okay. And we're going to form these 2. Oh, I can't see what I did up there. It's blocking it. Erase some of these so we can see it. There you go. All right, perfect. So we attacked that double bond, and the double bond was right there. So we put a Br on the left, the H goes on the right. We put a Br on the right, the H goes on the left. Okay, so now we're going to look at our products. And we're going to determine if it's going to be 50-50 or major minor. And then which one is major, which one is minor, if it is. So looking at those 2 compounds, seeing how the hydrogens are arranged, what would you say we're going to end up with?
50-50.
50-50. Perfect. Okay. Because if you look at each one closely, look at the top one, you'll see when the hydrogen's added, it has 1 hydrogen attached to the same carbon. Look at the bottom one. When the hydrogen is added, there's 1 hydrogen attached to the carbon where the hydrogen was added. So it makes no difference. Hydrogen likes hydrogen, but there's only 1 in each one. So it's going to be 50-50. Okay, because the amount of hydrogen are the same no matter where the hydrogen attaches to. Okay. So we look at the compound on the top, and that's our 2-methyl-3-heptane. Now it just becomes heptane. There's a methyl group at number 2. That hasn't changed. And now we've got a bromine at number 3. So this is going to be 50-50. And it's going to be 3 bromo, 2-methyl, heptane. Remember that this 3 goes away, right? Because the double bond's gone. And it's speaking ANE ending. Okay. So 50%, and you got 3 bromo. Remember the alphabetical order. B comes before M. It's missing a dash in here. It should be a dash right there. I'll have to add that in there. Okay. So 3 bromo, 2-methyl, heptane. And the bottom one. Who wants to name the bottom one now, since we know how to name it now?
It's 4-bromo-2-methylheptane.
Perfect. Perfect. 4-bromo, 2-methylheptane. And there should be a dash right here. In between, a dash between numbers and letters. All right, perfect. Ethene. Ethene is how many carbons?
2.
2 carbons. So the double bond has to be between the 2 carbons. Can't go anywhere else. That's all you got. Oops, what happened to my screen? I think I hit something. CH, 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 CH. Okay. So there's no way, I mean, it's going to attack, it's the hydrobromination still. So we're going to attack this carbon and this carbon with an H and a Br. Now looking at your molecule, your reactant, those are all hydrogen. Is it symmetrical or asymmetrical?
Symmetrical.
It's symmetrical. So it doesn't matter where the hydrogen bromine attack, it's going to be the same compound. So you're only going to have one answer. Doesn't make any difference where those attack. There's only going to be one possible solution because it's the same no matter what. It's a symmetrical, it's a perfectly symmetrical carbon. There's a perfectly symmetrical molecule. There's two hydrogens on one carbon. There's two hydrogens on the other carbon. That means no matter where we put the HBr, whether I attack HBr or BRH, it's the exact same thing. Just flip it around in space and it's the same compound. So you're only going to get one compound. You put the hydrogen in the bromine, and then you get one bromo or bromo ethane. You converted ethene into ethane. Okay, and you form bromoethane. There's no major minor. There's no 50-50. There's just one compound. So if you see a true false question that says true or false, hydrobromination of ethane produces two compounds that are 50-50, what would you circle?
False.
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 False. That's a hint. So understand the difference between major, minor, 50-50, and only a single compound. And remember, if it's symmetrical, it's only going to form a single compound. Can't form anything else because it's completely symmetrical in space when you rotate it. All right. Alkene reactions. That's what we've been talking about. Okay. Predict the major product in each of the following reactions. Name the alkene reactant and the product using the IUPAC nomenclature. All right. Here's our first example. This is 2-butene. Okay. And we're going to add hydrogen to it in the presence of nickel as a catalyst. Okay. You want to name the reactant, draw the product, and name the product. I think the next slide has all the information on it, but so this is, I already named this before I didn't run that. 2-butene. Is that correct?
No, it's trans.
Very good. Perfect. It's trans 2-butene. Because the CH3 groups or the hydrogen are opposite sides of double bond. Perfect. Okay. So we add hydrogen. What are we going to get? We're going to have CH3. We're just drawing a straight line here. And then I'm going to add, this is where I'm adding to the double bond now. I'm going to add a hydrogen on one and a hydrogen on the other. So what's the name of the product that we formed? Who wants to name this thing? It's 4 carbons, all hydrogen, single bonds.
Butane.
Butane. That's it. Perfect. We formed butane. Okay. Is it cis-butane or trans-butane?
It's neither.
It's neither. You cannot have a cis-trans isomer if you have only single bonds. You have to have a double bond or a cyclical structure to have a cis-trans isomer. Okay. No other way to do it. So this is just butane. Perfect. Okay. And that's exactly what we did. We added hydrogen, H to each one. We started with trans 2-butene and we ended up with butane. Okay. Predict the major product in one reactions. Name the alkene product using nomenclature. All right. Here's another reaction. This is a hydration reaction. Okay. So hydration means we're adding H and OH across a double bond. Okay. So here's our double bond. And is it symmetrical or not symmetrical? Is it the
Not
exact same?
symmetrical.
Right, it's not symmetrical because it's different on both sides of double bond. Okay, so we're going to add an H and an OH, and we're going to add an OH, and we're going to add an H. Okay, just how we break it up. It's going to go on different sides. So we're adding H2O, presence of a strong acid, and what product's going to form? Okay, it's going to form two products there, right? And those are two products. We've added an OH on the left. We added an OH on the right. There's our hydrogen on the right, hydrogen on the left. Okay, so everybody should understand that when you're adding hydration, now you're adding different things. It's not like hydrogenation where you add two hydrogens. Two hydrogen be the same thing because H is the same as H. Okay, with hydration, you're adding one side OH, one side H. So you can form different products if the starting compound's non-symmetrical. So there's our two compounds. And we want to know, is it going to be 50-50? Is it going to be major minor? Is it going to, and then we have to name these things. So let's look at the products that we formed. And are we going to be major minor? Or are we going to be 50-50? Which one? Anybody want to take a stab at it?
Major, minor.
Okay. Major minor. I'll agree with that. It's not quite as obvious as the other ones, but if we look at where the H is, look at the top one. This is the carbon where the hydrogen is bonded to. It has one hydrogen attached. This is the carbon where the hydrogen bonded to the bottom one. It has 0 hydrogens attached. Remember, hydrogen likes hydrogen, or Karnakov's rule. Okay? Hydrogen likes hydrogen. This is going to be your major product. Okay, so let's name everything we have here. Let's look at what we're starting with, and let's name that thing. So there's 1, 2, 3, 4, 5, 6, right? 6 carbons. 6 carbons. Okay, so it's a what? What's 6 carbons?
Hexene.
Okay. It's going to be hexene. Okay. And the double bond is at what carbon?
Two.
Number 2. So it's 2 hexene. And there's a methyl group at number 2 also. So 2 methyl, 2 hexene. That's what we're starting with. And we're going to end up with, you don't know how to name alcohols yet. So, but there's going to be still 6 carbons. And there's still number 2. It's going to still be 2 methyl. We still have the 2 methyl group. And it's going to be 2 hexane ol, O-L-N-D. OL just means it's an OH group. And we haven't done that yet, but we will coming up. It's just so you know. And the same thing on the bottom. It's going to be 2 methyl 3 hexanol. Okay. So 2 methyl 2 hexene. And like we said, this is the major product. Okay? Because we have this hydrogen right here attached to that carbon the other hydrogen bonded to. And it's 2 methyl 2 hexanol. If we break it down less before, the OL just means it's an OH group. That means alcohol. That's our next chapter. Hexane means 6 carbons, all single bonds. The number 2 position refers to where the OH group is. And then we have a methyl group at number 2. And the bottom one is going to be the exact same thing, except it's going to be 2 methyl 3 hexanol. There's an OH group at number 3 position. And that is your minor product. Because the carbon where there's hydrogen here on this one does not have any hydrogens except for what we added. So that's going to be our minor product. Okay. Let's do the same thing again here. All right. Take a good look at that. And now we're doing a BR2. We're not doing so it's bromination, not hydrobromination. We don't have hydrogen in it anymore. Right? So we're adding BR2 to this. So it's going to tack right here and right here, both sides of double bond. And it's going to add a bromine and add a bromine. Okay. Are we going to have major minor? Are we going to have 50-50? Or are we going to have a single compound?
Single compound.
Single compound, because we're adding the same thing to both sides. It's gonna make no difference. So we're just gonna form one compound with the two bromines attached to it. So here is your double bond. We open this double bond up and we added our bromine and add our bromine. That's it. That was an easy one. So what's the name of the starting material? Take a look at that. Someone want to give me a name for that? How many carbons in the longest chain?
2-methyl 2-butene.
Perfect. You got it. 2-methyl 2-butene, because that's number 1 carbon, number 2, number 3, and number 4. So we have a methyl group at number 2, and we have the double bond number 2. So 2-methyl 2-butene. We have 4 carbons across. That's where butene comes from. Okay, now we add our bromines to it. Okay, so again, our groups are 1, 2, 3, and 4. So what's the name of the product being formed from the bromination of 2-methyl 2-butene?
2-bromo, 3-bromo, 2-methyl butene or butane.
Good, good. The only thing is put the bromines together.
Dibromo.
So yeah, dibromo. So 2,3-dibromo 2-methyl butane. Okay, stick your bromines together. But you got it. Good, very good. Okay. So this is 2-methyl 2-butane and 2,3-dibromo. Remember, put the bromos together, and then 2-methyl butane. But all substances are the same together, and you got it. So on your exams, the question's going to read. The question will say, if I react 2-methyl 2-butene in the presence of bromine gas, what product will be formed? Give the name of the product. That's what it'll say. So you got to come up with all this, and then you got to name this compound. That we have to. I make sure you know how to do all the work with that. That's how the question is going to be phrased. Okay. Predict the products again for each one. And this is going to be a hydrohalogenation with hydrogen chlorine, hydrogen chloride. Okay. So we want to name everything. We want to do this. Take a good look at it. So what are the two things that are going to be added across this double bond? We're going to add an H and a Cl, or Cl and an H. Switch sides because you can go both sides. So we're going to take a look at that. We're going to open the double bond up, and we're going to add an H and Cl across that double bond. I think we're going to do that. There it is. Okay. So the same thing we started with. Okay. So we take an H and we took a Cl, and then we switched it to. So here's your double bond. It was right here. You opened it up, added our chlorine and a hydrogen. Added our hydrogen and a chlorine, left to right. Okay. So take a look at it and tell me if it's going to be a major minor or if it's going to be 50-50. What do you
Major,
think?
minor.
Major minor. And according to the textbook, what's always on top? Major one, right? All right, it's a major one because, not because it's on top, because there's 2 hydrogens attached to the carbon. And here's only 1 hydrogen attached to the carbon where the hydrogen added. And according to Markovnikov's rule, hydrogen likes hydrogen. So this is our major. This is our minor. All right. And I'll rename the first one. So it was 3,3-dimethyl 1-butene. Remember, you give the double bond the lowest number possible. So 1, 2, 3, and 4. So 3,3-dimethyl 1-butene. So let's name the top one. Be careful when you name it, Because remember, it's switched now. Who wants to give it a try? Any takers?
Is it 2,2-dimethyl 3-chloral butane?
Perfect, except alphabetical order. The chlorine comes first. But you got everything right. You got all the numbers
Yeah.
right. So it'd be 3-chloral 2,2-dimethyl butane. Very good. Most people still put it as 3. So they don't realize that the order's changed now because it's substituent, the lowest one, and there's no double bond. So perfect. 3-chloral 2,2-dimethyl butane, and that's your major product. The minor product is going to be what? Remember, you're going to switch back again now.
Four chloro 2,2-dimethyl butane.
If you're numbering left to right, well, now we're not. We're going to number right to left now, because the chlorine gets the lowest number. So it's going to be 1-chloral 3,3-dimethyl as it comes across. Because remember, you use your substituents the lowest number possible. Okay, this way it would be 2. This way it's 1. So the top one you went left to right. The bottom one you're going right to left. So don't get confused with those. Remember, you always want to give that substituent the lowest possible number. And this is on number 1. Okay, here was number 2 was the lowest possible number. Does that make sense? Or is that confusing everybody?
Yeah, now I'm confused.
Are you confused?
Yeah.
Okay, so let's go through it again. Let's get rid of some of these markings I have on here, so we can just see what we've got left over. Okay, if we're going to name the top compound, okay, we're going to give the substituent the lowest number possible. So we can either go left to right, 1, 2, 3, 4, or we can go 1, 2, 3, 4, right? If we number it left to right, the methyl groups get number 2 and the chlorine gets number 3. So there's 2 substituents that get the lowest number. Okay, so you number this one left to right. Does that make sense? You're going this direction because you'd have 2 substituents at number 2, 1 substituent at number 3. So the lowest possible combination is putting chlorine at number 3 and 2,2-dimethyl. But this way, if we number it this way, the lowest number is number 1 here for the chlorine group. The other way, it would get a 2 if I label it left to right. So we're going to label this one right to left, the top one left to right, bottom one right to left. Because we want to give the substituent the lowest number combination possible. And this gives a 2, 2, and this one gives a 1 for our lowest number. Does that make more sense?
Oh, okay. So I see. So the lowest number, as in, it doesn't matter which substituent, as long as it has the lowest number.
Correct. Doesn't matter
Okay.
what substituent.
Okay.
And the double bond's gone now, so we can't use that to count it. Okay?
Right. Okay.
Right.
When the methyl isn't the first constituent, is it because it's larger?
Whoa. Say that again?
Methyl, how come it's not a larger constituent? Is it because it's larger than the chloro?
No, because chlorine's at number 1. It doesn't matter how big it is. Chlorine's at the number 1 carbon. Methyl's at the number 2 carbon if you go this way. And 1's lower than 2.
Oh, I got you. I was looking at that hydrogen as a carbon.
No, it's not. So this one puts it at number 1. Does that make sense now?
Yeah.
Yeah, it's kind of tricky. It's not, you got to really think about it a lot of times like that. Polymer is a little different reaction. We're going to take a unit. We're going to link it over and over and over to make a long string of whatever that unit is. That's all a polymer is. Okay. So polymers are macromolecules, or large molecules, and they're just repeating units of the same thing, which are monomers, which is the name of the unit. And we take this monomer and repeat it n times, just over and over and over as we bond to it, make out a string of it. Okay. They can be made up of thousands of monomers that are linked together. Okay. A lot of commercially important materials are addition polymers made from alkenes and substituted alkenes. Okay. Addition polymers are named for the fact they are made by the sequential addition of repeating alkene monomers. So we take that unit, we add another one, and just link it all together. And that's what makes a polymer. Okay. So here's our unit. Catalyst, heat, pressure, and we link it. There's one unit, there's a second unit, there's a third unit, and so on. And we link all these together up to 1,000 times, or maybe more. And it makes a long string, makes different compounds that way. The alkenes are your R group, could be a hydrogen, a halogen, or any alkyl group, depending what you want to make. Okay, and that's your addition polymer. It's being addition because the monomer is added over and over again as a repeating unit. Okay, some of the things that we make with these monomers. Okay, styrene. Okay, you get the polymers polystyrene, and you can see the base unit right here, and it's repeated over and over. And we use that for styrofoam containers. Okay, acrylonitrile. Okay, or not making clothing. Okay, methyl methacrylate is just a pretty unit over and over and over again. Okay, it's used in basketballs, backboards that they make like that. It's also used in nail salons. Remember that distinctive smell you get in a nail salon? That's methyl methacrylate. That's the material they're coating on a polymer over the nails to give it strength and give it that glossy appearance. Okay, vinyl chlorides are made that way. There's your repeating unit. And that's plastic pipe, credit cards are all vinyl chloride. Okay, tetrafluoroethane, here's your repeating unit. Okay, and that's Teflon. Okay, put that on pans to make nonstick surfaces. It's an addition polymer that's coated over the pan. It's that same unit over and over again, which allows it to be nonstick on the surface. So it's some of the use of the polymers that we use in this addition polymerization. Aromatic hydrocarbons. Okay, remember aromatic we talked about? Aromatic is a benzene ring. Okay, benzene was first proposed 150 years ago. That was the structure of it. It's a cyclical structure, and the molecular formula is C6H6. Okay, there's something special about benzene. Okay, its structure has double bonds, but the molecule did not react as if it had any double bonds. It doesn't react like it's unsaturated. So it reacts like a saturated compound. This is worthy name or aromatic compounds because they smell nice. Okay. When things have benzene in it, they smell nice. Now you got to be careful with nice things that smell nice sometimes. Back in the 1960s, benzene was used as a disinfectant in hospitals and a lot of office buildings, stuff like that, because of its nice smell and its disinfectant properties. It turns out a lot of the janitors, we had this overwhelming high number of janitors dying of liver cancer. And sure enough, benzene is carcinogenic when you smell it. So if we use benzene in organic labs, which we do use, we use it in a hood, and you make sure you do not smell it because benzene is an extreme carcinogen. Right? So just because it smells nice and work doesn't mean we're going to use it all the time for cleaning buildings. Okay? Aromatic hydrocarbons are characterized by higher chemical stability than predicted by their chemical structure composition. In other words, they should have 3 double bonds in there, so it should react. We should be able to add chlorine across it. We should be able to hydrate it. We can't. Okay, there's something special about that benzene structure. Okay, the most common group of aromatic compounds is based on the 6-member ring, 6 carbons, benzene, and its structure. Okay, there's 6 carbon atoms. There's 6 hydrogen atoms. And it's a planar hexagonal arrangement. Each carbon is bonded to 1 hydrogen atom. There's 2 equivalent structures you can write. Those are called Kukla structures. They're recognized today as resonance structures. We talked about resonance structures. We talked about the different Lewis structures and the different stability those ones had, like the carbonated ion, CO3 2 minus, nitrate, NO3 2 minus. Those are resonance structures that give them their stability. That's what makes them strong acids. So the real benzene molecule is a hybrid. This we talked about in class last semester with Chem 3. It's a hybrid, which means it doesn't exist as we draw it, but it exists as a combination between those two structures. So each resonance structure, if there's two resonance structures, each bond is 50%. If there's three resonance structures, each bond is a third, 33%. Okay, so this is benzene. 6 carbons, all in one plane. Now you could draw the same way with the double bonds. Instead of here, you can put it here, here, and here. So that's a resonance structure where all you're doing is moving the bond. Okay, that's what gives benzene its strength. Okay, we usually write it. It's usually drawn just like this. Hexagon, and then conjugated. It's called conjugated double bonds. Every other bond's a double bond. But in reality, you could draw it either way with like the right or the left shows it. There's no difference. In reality, it's this. It's all these bonds being shared, which gives it its strength. The whole thing is shared across it. Every single bond in benzene is exactly the same. In other words, this is not a double bond and this is a single bond. Both are 1.5s. They're hybrids. So everything is shared and extremely stable. Extremely difficult to add things to a benzene ring. Okay? But it gives bonds a lot of strength, and there's different ways of representing it. All those things, and this is the most common way right here that you see benzene. Okay. Now, being given that, nitroglycerin is based on benzene, because if we break those bonds, we get a tremendous amount of force being released because they're extremely stable. Benzene, TNT, trinitrotoluene, is benzene. It's a benzene ring. I'll show you all those different structures too. Okay, because it's so stable. If when you break those bonds, a tremendous amount of energy gets released, and that's your explosion. Okay, this is how we're going to draw it for our class right here. But it's the same, and any of these are exactly the same thing. That's what it means. I mean, this is not a double bond. This is not a single bond. It's a hybrid, just so you know that when you see it. It's called a conjugated bonding system. Conjugated, if I can spell. Okay, means every other bond is a double bond. It's conjugated. Okay, just remember it's a hybrid. Okay, so the modern concept of bending is based on overlapping orbitals. Remember S, P, D, F, all those fun orbitals that we did in Chem 3? The p orbitals, the pi bond orbitals overlap and form this stable structure. So each carbon is bonded to 2 others by sharing a pair of electrons. Okay. The same carbon atoms share a pair of electrons with a hydrogen atom. Okay. The remaining 6 electrons are located in your p orbitals. The pi orbitals allow you to go above the ring. Okay, and form a stable ring structure around it that keeps this thing planar. Remember we talked about glucose, C6H12. You have the boat structure and you have the chair structure, how they're more stable. This doesn't do that. This is locked into place as a solid planar hexagonal structure because of those p orbitals. Okay, the p orbitals are perpendicular to the plane of the carbon ring. So the carbon ring sits here, the p orbitals sit like this above it, and they lock it into place all across the ring. They're perpendicular to the ring. So the p orbitals overlap laterally. They form this cloud of electrons above and below the ring, which makes it extremely stable. Okay, so the pi cloud formation, your p orbitals. Okay, so this is our model of benzene. You can see here, remember the s orbitals are your sigma. This is your s orbitals. That forms your single bond. Okay, your pi orbitals go above and below the bond, and they form a ring, okay, completely above and completely below. You see this ring of electrons. So it's being compressed by electrons at the top and bottom, and make this thing extremely stable. Okay, and it's just your pi orbitals causing that structure in benzene from the conjugated bonding system. Okay, and we name it as benzene. We put an NO2 group on it, this is nitrobenzene. If we put an ethyl group on it, this is ethyl benzene. If we put a bromine group on it, this is bromobenzene. If you put a chlorine group on it, could you tell me what it would be called?
Chlorobenzene.
Chlorobenzene, got it. Okay, so we name it as a benzene ring. Now we're going to change a little bit of that depending on what we do, but for the most part, we name it as a benzene ring, which makes it very simple. Benzene compounds do not undergo the same kind, they only undergo reactions, but not the same kind of reactions we're used to, not the same addition reactions. Because in reality, there is no double bond to attack. You got to remember that bond is spread out through the entire compound. So there is no double bond that you can attack in real life. Okay, I know we draw it like one, but in real life, that's a hybrid system and you can't add to it because they're not going to find it to attack. So you don't have the same addition reaction that we did for alkenes and alkynes. We have different types of reactions using different types of catalysts to help the reaction along. Okay. So remember, we took ethane, we added ethene, I'm sorry, took ethene, added bromine, we put a bromine on each one because it attacked the double bond. Okay. If you had bromine with benzene, no reaction occurs because this is not a double bond. In reality, it's shared. So it shares itself all around this ring structure. Okay. And if it's shared, there's no particular place for the bromine to attack. Okay. So even though we represent it as double bonds, it's really not a double bond in real life. It's a conjugated hybrid system, which makes it great, gives it great stability. So as we name benzene, a simpler amount of compounds are named as derivatives of benzene. Okay. For monosubstituted benzene, I mean, we add one thing to it. You name the group and then add the word benzene, like chlorobenzene, bromobenzene. Okay. Okay. So the first one would be chlorobenzene. Second one would be nitrobenzene. Okay. Third one would be ethyl benzene. Okay. Now, if we have a benzene ring, and we did, well, let me do that. We get it a little bit later. We'll get into that with toluene. When you have two substitutions, you name the groups in alphabetical order. Okay, just like the same nomenclature that we've been doing. So the first group is named at the position number 1. If there's a special group, it must be number 1 on the ring, like toluene, phenols, or benzyl groups. Those are special groups you can add to a benzene ring. I'll show you exactly what those are. Okay. An older system of naming groups using, okay, you can have ortho, meta, and para. Okay. All that means is the positions on the ring. Okay. And you still see this a lot in nursing nomenclature for different medications, things like that. So you see ortho, meta, and para. If you have a benzene ring, and we've got, say we got chlorine here and a chlorine here. That's orthochlorobenzene. Ortho means there's a substituent at the number 1 and number 2 position. Okay. Okay. If we had a chlorine group here, that would be meta chlorobenzene. Meta means it's the number 1 and number 3 positions on the ring. If I have my chlorine down here, that would be para dichlorobenzene or parachlorobenzene. It's at the number 1 and number 4 positions on the ring. Okay, if you count the ring, you do 1, 2, 3, 4, 5, 6 carbons. So if it's at the 1 and 2 positions, it's ortho. The 1 and 3 positions, it's meta. The 1 and 4 position, it's para. So ortho, meta, and para. Okay. So here we got 2 groups attached. an ethyl group, and a bromine group. Okay, so it's 1 bromo, 2 ethyl chloride. Why is it not 1 ethyl, 2 bromo? Because we name it in alphabetical order. Perfect. And we follow the alphabet. So this is 1 bromo, 2 ethyl benzene. Or what position is this? Is this an ortho, meta, or para?
Ortho?
Ortho. It's a 1-2 position. So you could also call it ortho bromo ethyl benzene. That means there's a bromine group at number 1, ethyl group at number 2, because the ortho is 1-2 relationship. So you could either say 1 bromo, 2 ethyl benzene, or ortho bromo ethyl benzene. Okay. We got a methyl group and a nitro group. Okay. So you could have 1 methyl, 3 nitro benzene. Okay. Again, alphabetical order. Or is this an ortho, meta, or pair relationship?
Meta.
Meta, 1 and 3. So you put meta methyl nitro benzene. Okay, so it could be meta, which is an M, methyl nitro benzene. Okay. And this one is a para, 1,4 position. So this would be 1,4 dichlorobenzene. Okay, or para, right? There's a para relationship, 1,4. Okay? Or it would be para dichlorobenzene. Okay, so some members of the benzene family have a very unique name that they were developed before the IUPAC system came into existence. And we frequently use those today. You'll see these different compounds. First one here is toluene with a CH with a methyl group on top. So you can call it methylbenzene, or the common name is toluene. Okay, the other one is an OH group. This is phenol. Okay, the other is an amine group. It's aniline or aminobenzene. Or you can have benzoic acid, okay, which is a carboxylic acid group. We haven't studied the carboxylic acid group yet. But toluene you should recognize. You don't get a blank page here. Here's xylene. Let's go back to toluene just a second. Toluene is the benzene ring with the methyl group on top. Now, toluene should sound familiar because I put on 3 nitro groups. I have got tri-nitro toluene, TNT. Remember I told you that benzene is very stable? With nitrogen compounds, you break those bonds apart, it's going to explode. And that's dynamite. Tri-nitrotoluene is TNT. Okay, so you just put 3 nitro groups on toluene. Let's see if I can get rid of that. Okay, xylene. Okay, xylene is 2 methyl groups. Okay, and you can have them at the 1,2 position, the 1,3 position, or the 1,4 position. So this is ortho xylene. This is meta xylene. This is para xylene. Okay. Again, your ortho, meta, and para positions of your substituent groups. Xylene is just 2 methyl groups attached. So ortho is at next 1,2. Meta is 1,3. Para is 1,4. All right. Creosol. Creosol is an OH group and a CH3 group. And again, you can have ortho, meta, or para relationships, whether it's 1,2, 1,3, or 1,4. So that's ortho creosol. Oh, mother. That's meta creosol. and that's para-creosol. Okay, name the following compounds using the IUPAC and Common Systems for Nomenclature. Name this compound. We have a chlorine group and we have a methyl group. Okay. You would name that 2-chlorotoluene. This is toluene. Remember, toluene has a benzene with a CH3. So there's toluene. So this becomes your number 1. Then number 2 is chlorine. So 2-chlorotoluene. Or you could put it as ortho-chlorotoluene because it's the 1-2 relationship. Remember, ortho is your 1-2 relationship. So 2-chlorotoluene or ortho-chlorotoluene. Okay. Remember, it has a nitro group here and an OH group down here. The OH group is phenol. Okay. So you would have 4-nitrophenol. This is your phenol group right here, your benzene ring with an OH. So that becomes number 1. Because phenol is the OH group attached. And this is at 1, 2, 3, 4. So 4-nitrophenol, or what relationship? It is ortho, para, or meta relationship.
Para.
Para. Okay. So it could be para-nitrophenol. Instead of 4-nitrophenol, it could be para. Because that tells you it's the 1-4 relationship. Okay. And we have an ethyl group and the NH2. Remember, NH2 is aniline. Okay. And this is a 1, 2, 3 position. Okay. So it'd be 3-ethyl aniline. 3-ethyl aniline. Or what position is this? Ortho, meta, or para?
Meta.
Meta. It's a 1-3 relationship. Ortho is 1-2, meta is 1-3, para is 1-4. So it'd be meta ethyl aniline. Let me tell you exactly where the constituents are. All right, same thing. Name the following compounds. Again, this is toluene right here. So this becomes toluene, and this is number 1. That becomes number 2. So 2-bromotoluene. Or is this an ortho, meta, or pair relationship?
Ortho.
Ortho. So the other name, or you could consider 2-bromotoluene. It could be ortho-bromotoluene. Okay, ortho is just an O. Because ortho is a 1-2 relationship. Okay. Now this is when you have toluene and we have phenol on here. So you can name it as the phenol group or the toluene group. So we'll name the phenol right here. This is phenol. And then 1, 2, 3, 4. So 4-methyl phenol. Phenol is the OH group on there. Okay. I would not mark you wrong if you put 4-hydroxy phenol, because hydroxy group is the OH group, because you name it as a phenol or toluene, or I'm sorry. You could also name it 4-hydroxy toluene, because the CH3 was a toluene group. Okay. The easiest way to do it is as a phenol group, it's 4-methylphenol. So ortho, meta, or para?
Para.
Para or para-methyl phenol, or it's called p-creosol. There's all kinds of different names for it. Okay. So again, here's aniline. Okay. And there's 2 attachments attached to it. So this would be This is always number one once there's a special function going like aniline. So 2, 3. So you have 2, 3 diethyl aniline. Okay, 2, 3 diethyl aniline. Or is this ortho, meta, or para? It's not. It's not either one of those. Ortho, meta, and para can only be used when there's two groups. You can't have three substituents. You can't have you don't have two substituents. If you have three, you cannot use ortho, meta, because there's a 1, 2 and a 1, 3. So you can't use that distinct percentage. So this is 2, 3 diethyl aniline. Now we can go back to ortho, meta, para. So here's our benzene ring. And 1, 2, 3. So who wants to name this one?
1,3-dibromo benzene.
Perfect. 1, 3 dibromobenzene. Or we could use ortho, meta, para. Which one we use?
Meta.
Meta. Perfect. Or meta dibromobenzene. 1, 3 position. Perfect. Now we can have benzene as a substituent, not as the main compound. We can have benzene hanging off a ring. Maybe we change the name a little bit. So when benzene's a substituent, it's called a phenyl group. Do not get confused with phenol and phenol. Okay, phenol is an OH group on a benzene ring. Phenol is a benzene ring attached to a hydrocarbon. Okay, there's your line structure. And it's phenol groups attached to it. Okay, so it's called a phenol group when it's attached. It's called a phenol when there's an OH group on it. Okay, don't get those confused. I know it's easy to confuse them. Okay, so note the difference between phenol and phenol. Phenol is when the OH group is attached to the benzene ring. Phenol is when it's a substituent, just like methyl or OH group or carbonyl carbon, when it's a substituent attached to a hydrocarbon chain. And we'll give you some examples. I wouldn't give me examples. So here's your carbon chain. Okay, and here's this benzene ring attached to it. So this is named phenol. We're just using the name phenol, not phenol, but phenol.
So is
do
that
a long,
two-
what's that?
Okay, never mind.
Oh, they couldn't make it more confusing, huh? They just switched one letter out and said, we'll just call it that. 4, 5. So it's a 5 carbon chain. There's a phenol group at number 4, and there's a double bond at number 1.
So
Five
4
carbons is-
phenylbenzene.
Yep, perfect. It's 1 pentene, so it's 4 phenol, 1 pentene. You got it.
So
Perfect.
even with something this large, the substituents take second place over the double bond.
No, double bond, the multiple bond with double and triple bond always take precedence over any other substituent.
Yeah, okay.
Yeah, you always, if there's no double bond, then this takes precedence. But if there's a double bond or a triple bond, that takes precedence. And then you name your substituents
Okay.
when you're numbering your chain. So this is 4 phenol, again, PHNEYL, 1 pentene. It tells you if there's a double bond, it tells you there's a 5 carbon chain. At the number 1 carbon is your double bond. There's a phenol group. Phenol means benzene when it's a substituent or attachment, and it's at the number 4 carbon. So it tells you exactly where it's at. Okay, let's look at this one. First of all, we get number left to right or right to left?
Left to right.
Left to right. You have the substituent lowest because there's no multiple bond. Okay, so 4 carbons, all single bonds is what?
Bromine.
Butane.
Butane, perfect.
All right.
4 carbon, no problem. Is 4 carbons butane, all single bonds. And at number 2, there's an attachment. What's that attachment called?
Phenyl.
Phenyl.
It's called a phenyl group. So put that together. It's 2-phenyl butane. Okay, so it tells you all the information's in the name. So it tells you A and E is a single bonds. Butane is 4 carbons. And there's a phenyl attachment at the number 2 carbon. Okay. Let's name this one. We can number the carbon chain left to right or right to left?
Right to left.
Right to left. Because of the double bond. Perfect. Well, you guys got this stuff. All right, and we have a substituent attached at the number 3 carbon. So what would the name of this compound be?
3-phenyl butane. Butene.
Perfect. 3-phenyl, 1-butene. There's the double bonds at number 1 position. So 3-phenyl, 1-butene. You got it. Okay, one final special name occurs in aromatic compounds is the benzyl group, Benzyl. When you have a CH2 group attached with something else over here, this unit right here is called benzyl. So if you put a chlorine on the end, it'd be benzyl chloride. If you put a bromine on the end, it'd be benzyl bromide. Okay, so this is the benzyl group. Okay, so again, here's the benzyl group that's circled, and then we added a chlorine to it. So that'd be benzyl chloride. Okay, an OH group attached to it. OH group is an alcohol. Okay, so benzyl alcohol. Again, this is benzyl, and the OH is a functional group for an alcohol. So benzyl alcohol. Draw each of the following compounds. Okay, now we're going to work backwards. Remember I told you organic chemistry, always go backwards. Going backwards is benzene. So draw a benzene ring. Benzene is that's benzene. Okay. And then it says there's chloral, and there's 3 of them. So there's 3 chlorines. And where are they at? They're at 1, 3, and 5. That's what you would draw. Okay, draw your benzene ring. Chlorines at positions 1, 3, and 5. Okay. Like I said, just make sure you work backwards in organic chemistry and you do just fine. Orthocreosol. Creosol was a CH3 and an OH group. Okay. So draw your benzene ring. And CH3 and OH, ortho means what? 1, 2, 1, 3, or 1, 4?
1, 2.
1, 2. Okay. Get that, otherwise you can see it there. So an OH group, oops, I hit the red button. OH group and a methyl group. That's creosol. And the ortho position is 1, 2. 2,5-dibromophenol. Phenol is benzene. Anybody remember what the group is with phenol? Phenol means OH. That's a phenol group, benzene with an OH. And then we get 2 bromine groups at numbers 2 and numbers 5. Whenever there's a specialty group attached, it's always number 1. Okay. So there's a bromine group at number 2, 3, 4, and a bromine group at number 5. So that's 2,5-dibromophenol. phenol. Okay. Again, that's always number one with the specialty group. That's your phenol group. And there's two attachments, and number 2 and number 5, and they're both bromine substituents. Okay. Para dinitrobenzene. So again, draw your benzene ring. You're gonna get good at drawing hexagons in this class. Okay, there's benzene, and it's 2 nitro groups. So NO2 groups, and they're in the pair position. So there's nitro, and then this would be ortho, this would be meta, and this is para, 1,4 position. Para dinitro benzene. Okay. Yeah, you got your benzene ring, and then 2 nitro groups at the para position, which is 1,4. 2 nitro aniline. Aniline is benzene with a NH2 group. That's aniline. Okay, so there's your aniline right there. There's your structure. And your specialty group always gets a number 1 position. So at number 2, there's a nitro group. Okay. This could also be called ortho nitroaniline. It's a 1,2 position. Okay. Picture, there we go. It's a little better picture. Okay, so here's aniline. Benzene with an NH2 group, and here's your substituent nitro attached to it at the number 2 position. M, nitrotoluene. Toluene is benzene with a methyl group attached. That's toluene. Meta means 1,3 position. So at the 3 position, you have a nitro group. Okay. That would also could be 3 nitrobenzene or meta nitro. I'm sorry, 3 nitrotoluene or meta nitrotoluene. Okay. So again, this is toluene. And your attachment is at the number 3 position, which is meta. 1,3 is meta. Okay. Okay, draw each of the following compounds. Draw 2,3-dichlorotoluene. So we'll draw toluene. Toluene is a benzene ring with a CH3 group. There's toluene. And then there's 2 chlorines attached. Again, with this, where this is a specialty group, this is always number 1. So this is 2, and this is 3. And each one is a chlorine. 2,3-dichlorotoluene. Yeah, this is toluene right here. And you have 2 attachments to it. And it's at number 2 and number 3, and they're both chlorines. So 2,3-dichlorotoluene. 3-bromoaniline. Aniline. Is NH2. There's aniline. Then we have number 3, there's a bromine attached to it. So 1, 2, that's number 3. So again, this is aniline. This is the structure of aniline here. Benzene ring with an NH2 group attached to the top. And then there's a substituent at number 3. What could this also be named?
Meta,
What's another
bromo,
name you could use?
aniline.
Perfect, perfect. Meta, bromo, aniline. Because meta just means a 1,3 position. Okay. 1 bromo, 3 ethyl benzene. My recliner chair works too. Cool. All right, so you have benzene. Again, always work backwards. Okay, so there's your benzene ring. At number 3, there's an ethyl group. So let's just put 3 down here, which is fine. And ethyl is 2 carbons. And 1, there's a bromine group. So again, here's benzene. Your attachments at number 1 and at number 3. 1 bromo, 3 ethyl benzene. Okay, or like you said before, meta bromo ethyl benzene, because you wouldn't have any other numbers. So you meta bromo ethyl benzene. That's a B. Okay, same thing. Meta means a 1,3 relationship. So either one of those would work for drawing that compound. Okay, ortho nitrotoluene. Toluene is benzene ring with a CH3 group at the number 1 position. That's toluene. Then it tells you there's an ortho relationship for nitro. Ortho means 1,2 relationship. So the substituent would be at the number 2 position, and it's a nitro group. So here's toluene. And here's your nitro substituent in the ortho position. Over here would be meta. There would be para. And this is your ortho position. P-xylene. Xylene was a CH3 and an OH group attached. So you'd have benzene with an OH group and a CH3 group, and it's in the para position. So para means 1,4. So the methyl group would be in the 1,4 relationship, and that's P-xylene. Oh, I'm sorry. I was thinking that it's xylene is 2 CH3 groups. So this would be CH3. I was thinking of creosote. My mistake. So xylene is 2 CH3 groups attached, and it tells you the pair position is at 1,4. Okay. So that's para-xylene. Dibromo, ortho-dibromobenzene. Okay. So benzene. Okay. There's your benzene, right? That's this part of the compound. And then there's dibromo, which means 2 bromines. And ortho. Ortho means what? What positions?
1, 2.
1, 2 position. Perfect. That's ortho dibromo benzene. Polynuclear aromatic hydrocarbons. Whole new class of compounds. So polynuclear aromatic hydrocarbons are called PAH, are composed of 2 or more aromatic rings joined together. Okay, polynuclear, so more than 1 aromatic hydrocarbons. So if you have a benzene ring, let's just give an example. like this. You can have another benzene ring like that. And it's here in the center. So those are more than one aromatic hydrocarbon rings joined together. Okay. Many have shown to cause cancer. Okay. They're a lot worse than just benzene. Benzopyrene is one of the most potent carcinogens known that we know of. Extremely carcinogenic. It's found in tobacco smoke, car exhaust, and charcoal grilled meat. Is where you found the benzopyrenes. Extremely carcinogenic. So tobacco smoke, car exhaust, charcoal grilled meat all have benzopyrene in them. Okay. And this is what benzopyrene looks like. Multiple units of benzene joined together. Okay. You also have naphthalene, anthracene, and phenanthrene. Okay. You can see the different polymatic hydrocarbons, how they're joined together. 2 rings, 3 rings, 3 rings at an angle, or 5 rings. How they join up together. Okay, so benzopyrene. Let's take them each separately. One of those potent carcinogens known, like we said, found in tobacco, smoke, car exhaust, and charcoal grilled meat. Smoke also contains carcinogens. Okay, primary of concern, those with chronic exposure, cigarette smoke. Okay, you're exposed over and over to it. It's extremely potent carcinogen. So all fires generate benzopyrene. Okay, no matter what, smoke from any fire is going to generate benzopyrenes. Classical chemical initiator of carcinogenesis, as well as hundreds of others polymatic hydrocarbons. Some of which are known to be promoting agents, to promote genetic defects. Okay. These chemicals are responsible for the increased incidence of lung cancer in tobacco smokers and have been linked with an increased risk for lung cancer in foundry workers where there's smoke. Okay. Inhaling smoke from any cause can contain these benzopyrenes, which increases your chances of lung cancer because they're inhaling it. The PAH present in soot were probably also responsible for incidents of scrotal cancer in chimney sweeps. More than 200 years ago, the English surgeon, Percival Pott, considered to be the first recognized occupational cancer. Okay. Again, the soot from fires caused a very high incidence in chimney sweeps in England, like about 200 years ago. Whether or not others with occupational smoke, okay, like blacksmiths, firefighters, or cancer, the studies haven't been done. They haven't found that increase. The activated form of benzopyrene is the diol episide BPDE, and it causes DNA adducts, leading to point mutations and single-strand chromatid breaks. And we will study those in the chapter 21, I believe it is. The different types of point mutations, DNA, and single-strand chromatid breaks, of what these benzopyrenes can cause. Okay. A major concern that people who start smoking at a young age seem to have a greater amount of permanent DNA alterations than smokers who started smoking later on in life. Which the more you're exposed to it, the more point mutations and the more chromatid breaks you're going to have, and the more it's going to lead into different types of cancer. So a direct link has been established between tobacco and lung cancer through the effects of metabolite benzopyrene. This is the component of tobacco smoke. This is what causes lung cancer in smokers. Okay. There's 3 loci, okay, on the tumor suppressor gene. We'll get into tumor suppressor genes again. I think it's chapter 20 or 21 in this book. And you have genes that the body turns on, makes these proteins that suppress tumors, that stop cancer from occurring, okay? It damages 3 locations, the loci on the TP53 gene, the benzopyrene, okay? Okay, which are abnormal in 60% of primary lung cancer. So 6% of lung cancer patients have these damaged genes where they have the tumor suppressor gene or damage at these three locations. And that's how it works. Okay. Other polycyclic aromatic hydrocarbons found in smoke are likely to be involved in predisposing to genetic damage. So polycyclical aromatic hydrocarbons cause a lot of genetic damage and are all carcinogenic. They recently discovered that tobacco leads to an increase in the levels of COX2, a protein linked to cancer causation. Okay? So not only is it suppressing the tumor suppressor gene, so you're not making the tumor suppressor protein, but you're also increasing the level of COX2, which is a protein that actually causes cancer. Okay. COX2 inhibitors are no longer being studied as potential preventive agents because of the increased risk of serious cardiovascular disease. Okay. So if we make inhibitors to inhibit COX2, that stops it from causing cancer, we end up killing the patient with cardiovascular disease. Okay. That's what the agents that inhibit also cause. You can't make the cure worsen the disease. Okay. Naphthalene is another PAH. Okay. Naphthalene is found in mothballs and toilet bowl deodorizers. You know that real strong smell you smell with mothballs? That's naphthalene. Oops. Exposure to large amounts of naphthalene may damage, okay, or destroy. Okay. Some of these words are X'd out. I don't know why. It's the damage or destroyed sections of the DNA genes. Humans, boy, let's see if I can see it. There we go. I can read it this way. We'll do it this way. Some of those words are kind of funky. So naphthalene is found in mothballs and toilet bowl deodorizers. Exposure to large amounts can damage or destroy your red blood cells. Okay, humans, particularly children, have developed this condition known as hemolytic anemia. Okay, after ingesting mothballs or deodorant blocks containing naphthalene. So if your child eats mothballs or gets a hold of deodorant sticks, okay, that can cause hemolytic anemia. Okay. Symptoms include fatigue, lack of appetite, restlessness, pale skin. Okay, exposure to large amounts of naphthalene may cause nausea, vomiting, diarrhea, blood in the urine, and jaundice. Look at this to pick up some of those words that are being blocked out. So the Internal Agency for Research on Cancer classifies naphthalene as possibly carcinogen to humans and animals. Okay. The agency also points out that acute exposure causes cataracts in humans, rats, rabbits, and mice, and that hemolytic anemia can occur in children and infants after oral or inhalation exposure or after maternal exposure during pregnancy. Okay. So you can cause hemolytic anemia in a newborn if you're exposed to mothballs, toilet bowl cleaners, things like that with that strong smell while you're pregnant. Over 400 million people have an inherited condition called glucose 6-phosphate dehydrogenase deficiency. Okay. And we're getting a lot more of that in the next couple of chapters too. Exposure to naphthalene is more harmful for these people and may cause hemolytic anemia at even lower doses. People with this glucose 6-phosphate dehydrogenase deficiency. Okay. In China, the use of naphthalene in mothballs is forbidden, but not in the United States. But China has forbidden it because of the type of cancers it can cause. Go back. So anthracene is another PAH. Anthracene is used to make dyes, plastics, and pesticides. Okay. One of the most common ways of anthracene to get into the body is through breathing contaminated air. You breathe that in. Okay. Once inside your body, the anthracene appears to target the skin, the blood, stomach and intestines, and your lymphatic system. Exposure to high doses of anthracene, even for a short time, can cause damage to the skin. Okay. It can cause burning, itching, edema. Edema is just a buildup of fluids in your tissues. So humans exposed to anthracene experience headaches, nausea, loss of appetite, inflammation or swelling of the stomach and intestines. Okay. The reaction time slowed in a week, in addition to all those other symptoms. So a number of PAHs cause tumors in laboratory animals that were exposed to PAHs through their food or from breathing contaminated air or when it's applied to their skin. So this is an airborne carcinogen, okay, or it could be exposed by exposure to your skin or by applied to your skin. Phenanthrene. This is the other last PAH. Preparation of the opium poppy used for many hundreds of years to relieve pain. Okay, morphine. Okay. Toxic effects and added potential have been recognized throughout the ages, okay, as we use it for preparation of these opium poppies. Morphine was isolated in 1803 and later shown to be almost entirely responsible for the analgesic activity of crude opium. So morphine is the active ingredient. Morphine is recognized by our brain receptors, actually. The term opiate applies to the natural occurring derivatives of phenanthrene. Okay. It's an opium alkaloid, poppy, extract like codeine, thebaine, or morphine. An opioid.
Is Dilaudid a part of that same family?
Yes. Yep. Codeine, thebaine, morphine are all in the production of it. Yep. Different amounts will do different responses in the body. Codeine has a different response than morphine.
Yeah, because we were told that Dilaudid is one unit of Dilaudid is equivalent to 10 of morphine.
Right.
Okay.
Dilaudid is extremely strong form of morphine. Okay. And it all depends on receptor, just like heroin. Heroin's a form of morphine. Okay. It's a lot more addicting than morphine. It's kind of a weird study that they did with the rats. It turns out that for heroin to work, heroin has to be converted to morphine in the body. There's no receptors for heroin in our body. It doesn't do anything. Heroin converts to morphine, and the morphine binds to receptors in the brain, which gives you your high. Now,
So theoretically from that is for that particular individual, is actual morphine going to be more addictive for that individual because it doesn't have to be processed into morphine, it's already there?
you would think so. That's the logical conclusion, but it's wrong. Heroin's much more addictive than morphine because we have a blood-brain barrier in our body that things cannot get into the brain. The brain filters what gets, the body filters what gets into the brain. Heroin is very nonpolar. It passes the blood-brain barrier quicker than morphine does. And in the brain, then it gets converted to heroin and has its effect. So heroin has a quicker and more dramatic effect than morphine because it gets there faster. It can pass the blood-brain barrier, then it's converted to morphine and has its effect. Morphine has to go through the body, it has a long time getting through the blood-brain barrier. So it makes heroin much more addictive because it's such a faster, stronger high than morphine, even though it converts to morphine in the brain to have its function, which is really, it's the exact opposite of what you think would happen.
So in patients that have like difficult filtering things, is that why morphine would stay in the body for longer? Because like I've had patients, for example, that are given the morphine and then like 4 days later, they're still confused from the morphine because it hasn't been filtered efficiently enough.
Yeah, not just to filter, it doesn't resorb. A morphine acts as binds to receptors. If you lack the enzymes that break down the morphine in the body, that's going to hang around a lot longer. It's not going to be destroyed as quickly. So it will hang around by a lot longer, yes. And it could have parts that could be in the bloodstream. The dizziness or the confusion that has already passed the blood-brain barrier and is acting upon the receptors in the brain. But some people lack the ability to break down the morphine once it's in the body, and that can cause severe problems. And 4 or 5 days later, they can still be confused after giving 1 dosage of morphine. That's an enzyme problem. And we'll get into that in one of the chapters in like coming up also in the biochemistry part, which is really interesting. But it's really cool when you think about how it actually works. But these are all in the same group, codeine, thebaine, and morphine. They're different derivatives of it and different strengths. I mean, codeine is a lot different than morphine for pain control. Okay, just acts at different receptors. That answer all the questions?
No, you answered mine.
Okay, good, perfect. So an opioid is any drug that activates the opioid receptor, including both opiates and synthetic and semi-synthetic opioids. The ones that we make, ones that are natural, or ones that are kind of combination that we've derived chemically. Yeah. It activates receptors in the brain, causing that high that you feel. Okay. A narcotic is any drug that induces narcosis, a numbness or torpor, a downer, basically, is your narcotic. Okay. Those are the different polyaromatic hydrocarbons, the different effects that they have. It's a whole family of drugs and a whole bunch of lectures on coming up. So benzene, we talked about, does not readily undergo distant reactions. Okay? It's a very stable compound. Right. Benzene typically undergoes aromatic substitution reactions. So it reacts under different conditions with different catalysts. So an atom or group of substitutes for hydrogen on the ring. Remember, benzene has 6 carbons, 6 hydrogens. So we substitute a group, replacing a hydrogen on that ring. Okay. All benzene reactions require a catalyst because benzene is very stable. The reactions are halogenation, where we can add a halogen to benzene. Nitration, we add a nitro group. And sulfonation, where we add a sulfate group. Those are the 3 reactions we're going to deal with benzene. So halogenation replaces a bromine or a chlorine on the ring, replaces a hydrogen with either a bromine or a chlorine. We typically use bromine or chlorine, Br2 or CO2 to diatomic. Okay. And you use FeCl3 as a catalyst. Okay. Iron or iron chloride or iron, yeah, or iron 1 chloride. Okay. So you have benzene plus CO2 with iron 3 chloride, and you replace benzene with one of the hydrogen with a chlorine, and then HCl. So the chlorine splits. 1 chlorine goes here, kicks off the hydrogen. The hydrogen combines with the other chlorine to form HCl. Okay. Bromine, same way. You have bromine, Br2. That splits. One of the bromine attaches to here. This hydrogen is kicked off and combines with this other one to give you HBr. Okay. And here's how the reaction takes place. Okay. You can see the bromine bonds to the catalyst to form a bromine complex. This bromine complex right here transfers electrons, and from this double bond, it opens this bond up. Okay, once this bond is opened up here, you have the HBr attached to it. This bromine is looking for those electrons. Okay. And now you have a negative FeBr3 with bromine full complex because one of the bromines has been removed. Okay. This comes down along. This other hydrogen, the bond comes back down, reforms a double bond here. Okay. And this bromine forms here. And the hydrogen that's kicked off forms with that bromine to give you HBr, regenerate your catalyst, and now you've got a bromine substitute on the ring. This is how the electrons transfer during a bromine halogenation reaction. It binds to the catalyst, pulls the electrons away, makes it very electronegative, wanting electrons, and it goes after one of the bonds. Opens it up, treats it like a single bond for just an interim, okay? And puts your bromine right onto there and kicks the hydrogen off. And this is the product you end up with. Okay. That's how you chlorinate or brominate a benzene ring. Now, nitration of the ring is going to be similar. It places a nitro group on the ring. Okay. You need sulfuric acid as a catalyst. Sulfuric acid is battery acid. It's a very strong acid. Okay. So benzene and nitric acid. And here's your catalyst, sulfuric acid. Okay. You get the NO2 group from your nitric acid and puts a nitrogen group right on benzene, the NO2. And it gives you H2O as a byproduct. Because you got to remember, we got to account for all the elements when we balance it out. So HNO3, if you do NO2 attachment, this is your nitro attachment, you still have an OH left over, right? Sometimes you'll write this as HONO2 instead of HONO3. We'll write it that way because this is going to split right here. The NO2 is going to go to the benzene ring. The OH is going to take this hydrogen that got kicked off and add to it to give you H2O. So all our elements are accounted for. It's a balanced chemical reaction. Okay. That's right. So sometimes you write it as HONO2. So you can see where the water is coming from and where the NO2 group is coming from. Okay. And again, this is the mechanism of the reaction for it. You see the electrons being transferred. So the sulfuric acid causes a nitric acid to go to NO2, HSO4, and water. Okay. Remember, your sulfuric acid is your catalyst, so it has to be regenerated at the end of your reaction, and it is right here. Okay. Remember, catalyst has to be used, and then during the reaction it cannot be used up in the reaction by definition as a catalyst. It speeds it up or allows the reaction to occur by lowering its activation energy, and then it has to be released at the end so it can function again. So here's the first step. You're producing NO2, which is right here. NO2 causes the electrons to pull because oxygen is very electronegative. So it leaves a positive charge up here on the nitrogen because the oxygens pull the electrons away. That positive charge is attracted to the negative charge of the electrons in the double bond. Again, it's not really a double bond, but it attacks one of the bonds in any order, and it doesn't matter which one of the six. So this bond basically opens up right here, and you get what's called a carbocation, which is a positive charge on a carbon, which is very, very unstable. Okay. And then you get this complex form. Here's a hydrogen, the original hydrogen, and then the NO2 group attacks because it has a positive charge attacking to there. So now you got two bonds here, and you have what's called, like I said, a carbocation, which is a positive charge carbon. So that bond slings down here and closes that up because that's very unstable. Okay. That gives you your 4 bonds back to carbon, and it takes this water molecule and kicks it off. The hydrogen it forms to that. Okay. Gives you an acid. There's your NO2 group. And then the H3O reacts with this HSO4 that was generated here to reproduce your catalyst. Okay. Now these are really, I know you might not understand what I'm going to say, but go back and review it and you should understand. It's just, all this is a transfer of electrons due to electronegativity. And it's showing a proposed mechanism for how this works. Okay. I don't expect you to be experts in how this works, but you need to understand that these can happen and you can get nitration on a benzene ring, chlorination, bromination on a benzene ring by the use of a catalyst. And the catalyst is creating a group that has an extremely positive charge on it. That's attracting to the negative electrons. And that forces one of the bonds to open up. And from there you can get a substitution. Now remember, when these occur, you got to remember there's a hydrogen here and an NO2 group here. Either one of those can be resulted. This could be kicked off again and just put a hydrogen back. Okay, half the time the hydrogen's going to go there, half the time the NO2 is going to go there. It's not 100% mechanism on these things. Okay, it's just the electrons being attracted, and a certain percent of the time the hydrogen will kick off and the NO2 group will stay. Sometimes the NO2 group can kick off and the hydrogen will stay, and you won't have any reaction with it. Okay, these benzene compounds are not very reactive, and it takes a lot to get them going. And we have the last one is sulfonation. Sulfonation is sulfonation, places an HSO3 group on the ring. Okay. Concentrated sulfuric acid, extremely strong sulfuric acid, is required as a catalyst again. And it's also a substitution reaction. All these reactions with benzenes are substitution reactions. Okay? They're not what we've been doing in the past. They're completely different reactions, whole new mechanisms. Where you're getting electron transfers and they're being pulled by a catalyst to give you an electron deprived area that can now attack that bond rapidly. Okay, you've got to force these reactions to occur. Okay, so plus SO3 goes to HSO3 attachment. That's your sulfonation, your HSO3. So you do have an HSO3 attachment. Okay. High concentration of sulfuric acid, and it bonds to the benzene ring. Okay. This one's a real similar reaction to the other one. The sulfuric acid causes HSO4 minus, which we're going to use that at the end to regenerate a catalyst, just like we did before. So the SO3 ion, okay, again, this is what's called, this is a resonance structure, and it pulls the electrons away from the sulfur atom because oxygen is very electronegative, leaving a positive center. Positive is attracted to the negative charge of the multiple bond. That bond opens up. Once this bond opens up, the SO3 attaches. Okay. This leaves a deficiency right there. It leaves 3 bonds on the carbon, because remember there's a hydrogen still there. Carbon does not like 3 bonds. It likes 4 bonds. So immediately this bond slams back down there. And like I said, 50% will be the hydrogen, 50% will be the SO3 group. Okay. If it's the SO3 group that stays, the SO3 group stays attached, the hydrogen gets released, and this bond gets formed. Okay, you're in sulfuric acid, so the H bonds to this hydrogen, this oxygen here, okay, to get your HSO3, to get rid of that negative charge. Okay. So then you get your HSO3 and your HSO4 being generated, okay, and that combines with the acid from this, where did our hydrogen go? This hydrogen here, where it got kicked off, combines back with water to H3O plus, and then that regenerates your catalyst. I know they're confusing reactions, but just think about it in terms of electrons moving because something wants the electrons more. And if electrons move, electrons are negative. So when they move towards something, they create a negative charge. But in doing so, as they're pulling away, create that negative charge, it creates a positive charge where it left, because now it's electron deficient. And what it's looking for is something to fill that deficiency. And it's going to go after the benzene ring and pull it from one of those multiple bonds in the benzene ring. Okay? But that benzene is going to reform because it leaves such an unstable intermediate. Okay? I just want some kind of sense of that. You don't need to memorize all these mechanisms for all that, but just understand basically how it's working, with the difference in the electrons being shifted away, causing a deficiency, attacking the bond, causing a new one to form, and then one of those two is going to kick off. So one of these two kicks off every time to go back because this is such an unstable structure that's created. Carbon does not like to have 3 bonds, and it's going to immediately rectify that situation. And to also recognize that any catalyst has to be regenerated at the end of the reaction, or it's not a catalyst. Catalyst does 2 things: speeds up a reaction and regenerate, and is not used up in the reaction. Okay, rings at least 1 atom other than carbon as part of the structure of the ring of the aromatic ring. These are heterocyclic aromatic compounds. Heterocyclic because one of the atoms in the ring is not a carbon atom. Sugars have an oxygen atom in the ring. A ribose sugar, it's 5 structures, 4 carbons and 1 oxygen. Okay, your purines, your pyrimidines of DNA and RNA. Okay, these are heterocyclic aromatic compounds. Okay, the hetero atom is usually oxygen, nitrogen, or sulfur. That's the one that gets replaced inside the ring, because those allow for multiple bonds. The ring also has delocalized electrons, just like our benzene ring, to make them stable. It forms those pi electrons above and below the ring. The total number of atoms in the ring is going to be either a 6-membered ring or a 5-membered ring. Okay. So you're going to have 6 or you're going to have 5 elements in the ring. Okay. So heterocyclic aromatic compounds are similar to benzene, okay, because of their stability and chemical behavior. A lot of them are biologically active. Your purines and your pyrimidines are components of DNA and RNA. We're going to go over a lot of those in chapters to come too, the purines and pyrimidines. We're going to get into a lot of detail in DNA and RNA and how they work in the body and how they cause mutations, how they cause different functions. And I just hit the wrong key. Go backwards. Okay. Pyridine is found in nicotine. Pyrrole is in hemoglobin and chlorophyll. Okay, so here are some of your rings. Here's one of the rings. That's a heterocyclic ring. It has nitrogen replacing carbon of a 5-carbon ring. So there's 4 carbons and a nitrogen. Okay, this is porphyrin. Porphyrin rings make up hemoglobin. Okay, the iron in the center is bonded by those nitrogens as part of the heterocyclic rings, and that's what holds oxygen into the red blood cells, so it can be delivered to different parts of the body. The porphyrin rings is your structure that makes up of hemoglobin. Okay, so a heterocyclic aromatics is when a conjugated bonding system, like we saw in benzene, one of the carbons gets replaced by a different element. Nitrogen, oxygen, sulfur are the 3 typical ones. Okay, that's what heterocyclic aromatics mean. Okay, so here's a 6-unit ring where one of the carbons have been replaced by nitrogen. This is pyridine. Okay, there's a 6-unit ring, 6-unit cyclical ring, where 2 carbons have been replaced by nitrogen, and that's pyrimidines. Okay, here's a 5-unit ring where one of the carbons is replaced by oxygen. That's furan. And this is a 5-carbon ring where one of the carbons is replaced by sulfur. But again, you see it's a conjugated bonding system. Every other bond, single bond, double bond, single bond, double bond, single bond, double bond, double bond, single bond, double bond, single bond, double bond. It's all conjugated. So it's just like the benzene rings. It forms that stability because those pi electrons that can be shared above it. And that one's called thiophene. Okay, so heterocyclic aromatics are similar to benzene in both their chemical behavior, how they react, how they behave with different components, with reactions, and how stable they are. Okay, many are very significant, biologically important compounds. Okay, we said this was a pyrrole where nitrogen is found. This is found in hemoglobin, like we showed before. Hemoglobin and in chlorophyll. Okay, here's other ring structures. This is a pyrimidine. Okay, this is a purine, where you see the nitrogens is heterocyclic, where the nitrogens have replaced carbon in this 6-ring structure here, and this 5-ring structure here. Okay, and these are found in DNA and RNA. These are what make up your bases. Your adenine, your thymine, your guanine, your cytosine. They make the basis of DNA. Okay. The pyrrole ring is a component of the porphyrin ring found in hemoglobin and chlorophyll. That's what blocks in your iron. Iron is what attracts what builds with the hemoglobin. The hemoglobin binds the oxygen in the ring to carry to different parts of the body. Again, it's a conjugated ring structure. Here's a double bond, single bond, double bond, single bond, double bond, single bond, and so on. It's a conjugated system. Conjugated systems in chemistry are very, very stable. Okay. This is a review of all the reactions we covered, and that would be the end of the chapter. So alkenes, we talked about, undergo hydrogenation. You add hydrogen in the presence of platinum, palladium, or nickel, and you get hydrogenation. You can add water, presence of an acid, to get hydration. You can add hydrohalogenation reactions. to get a chlorine and a hydrogen, or two chlorines, get a halogenation reactions, two bromines, two iodines, etc. Those are reactions we talked about. So addition reactions, hydrogenation, hydration, and halogenation. Those are all addition reactions to alkenes, and hydrohalogenation. So in hydrogenation, we're adding hydrogen. Hydration, we're adding water. Halogenation, we're adding a halogen. Hydrohalogenation, we're adding hydrogen and a halogen. And the reacting those across a double bond. We get major minor products, we get 50-50, we get single products, all depending on what we're adding. Additional polymers like styrofoam cups, stuff that we make. Okay, so they're just, you're taking one unit and you're adding that over and over, making this long chain. This long chain polymer from these monomer units. Reactions of benzene we just talked about. Halogenation, there are three, remember, halogenation, nitration, and sulfonation. Okay, and those are very difficult reactions, require a catalyst, and it replaces, it's a substitution reaction. It is not an addition. Addition reactions are alkenes. These are substitution reactions where hydrogen, one of the hydrogens from this ring sector, is being replaced by either a nitro group or a halogen or a sulfur group, HSO3 minus. Okay, so hydrogenation, we add hydrogen to where the double bond was. Hydration, we add water across. And you have to add it to, and it could switch sides too. Halogenation, we're adding a halogen like chlorine or bromine across it. Hydrohalogenation, we're adding hydrogen with a halogen across the double bond. Again, and you can switch sides with that. And you got to remember major Malkonovic's rule of hydrogen likes hydrogen to get a major minor project. And this is just, you go back, you this a summary, it shows everything all in position: alkene, hydrogenation, hydration, halogenation, hydrohalogenation, and the addition polymers are alkenes, where you have this one unit and this unit gets repeated over and over and over as it bonds to itself. These are the monomers. Each monomer together to form a polymer. Okay, and it could be with alkyl groups, it could be with hydrogen, or could be with alkyl groups or halogens in that monomer. That's an addition polymer, and that's how it acts. It just forms these little bonds, and this unit repeats an amount of times. And the halogenation of benzene, replace it with a halogen, generated HX. Nitration, replace it with NO2, generated H2O. And with sulfonation, HSO3, we generated water in their sulfonation of benzene. We went over the different mechanisms of each of those. Okay. And here's your benzene reactions. Okay, this is your halogenation, this is your sulfonation, and this is your nitration. Again, it forms nitrobenzene, it forms benzene sulfonic acid, and it forms a halobenzene like benzoyl chloride. Okay, and there's your summary from the back of the book. Looks just like that. So you can refer back, get all your reactions in one place so you can see everything.